This is lecture 7 of graph theory. So in the previous lecture, we learned about diffusion processes on a graph, how we can compute the information flow efficiency based on a diffusion model by looking at random walks on graphs. So in this lecture, what we will learn about is how diffusion basically on graphs can be applied to other real-world problems. So we will look at the intersection between diffusion and the fields of machine learning and pattern recognition. And the application is to segment images, okay? So today's lecture will be based on studying and learning about this research paper. So it was published by Wang and co-authors and published in CVPR 2012, okay? So this is the paper. I will put the link down below the video so you guys can read the paper and access it. So I really recommend you have a look at the paper, okay? So and read it thoroughly. Now, let's look at how we can use diffusion to do image segmentation. So first, what is the problem that the authors wanted to solve in their research paper? So given an input image like this one, okay, the goal is to learn how to segment this image. So what does it mean? So for those who have no background in computer vision or pattern recognition, it's very simple. Segmentation means we want to label or extract, partition the image into different objects, okay, or different parts that are semantically connected. So segmentation means that we want to divide this image into different parts or different regions, and each region represents a particular object. For example, here we are segmenting this one. So you can see that this is, labeling only one part of the image, but we also need to label the background. So if we label the background, we'll get something like that. So you can see that the task of manual labeling, like what I'm doing like here, so there is like a human being, an expert who is trying to label all these regions. What is like kind of painful about this? It is what, guys? So imagine if I give you thousands of images and I ask you to extract different objects in this image. Do you think it's a fun task to do, just doing this? Well, it might be funny if you are in elementary school, right? But if you have lots of other things to do and you want to kind of spend time coloring and labeling like objects and images, this is not really fun. So this is a time-consuming task, okay? So the goal here is to teach a computer how to do this automatically, and for that we're going to use graphs. So in the field of machine learning, this is we can call automatic. Okay, let me just change the font. So we can call it automatic segmentation. Okay, image segmentation, or also labeling. Okay, right. Now, this is the problem that we want to solve. So we want to give our algorithm an input image, and actually it outputs what we call the label image or the label map. Okay, so this is our goal, to get the label map. Now, how to model this problem? So how can we possibly model this? Okay, so for example, here, what do you guys notice? Like when I'm coloring, how like if you try to come up with a strategy for automatically extracting this orange object right there, okay? How can we do that? How can we possibly do that? What is the implicit strategy that I adopted to do this? What was I following when I was coloring?
Which color?
The average color, the color, basically. Yes?
Each color has different gradient values.
Yeah.
When we diffuse the image,
okay.
There's a sharp difference between the images. We can understand there's an edge or a different object or something.
Right. So what I was like doing implicitly is trying to pick those the boundary where there is a big change, okay, between two regions, okay? So a big change in average intensity or in intensity. So you can see that these two regions are very different, okay? So once I know how to find the boundary, then I can easily find the object, okay? So this is one way. Now, in this lecture, what we will look at is how to model this problem using graphs, okay? So one idea is that the good thing about graphs is like we can model relationships, okay? So we can, define nodes, and then between these nodes, we can define a relationship that will allow us to achieve this task. So any idea on how can we use graphs, okay, in such a way that we can basically input this image and output the label image, okay, which is the segmentation map or the labeled image. How can we possibly use graphs to solve this problem? So you need to think, when I say this, how to model this problem using graphs. You need to answer two questions. What is a node in my graph? And what is an edge in my graph? What could it possibly be? Okay, if you answer these two questions, then you will know how to model or formalize this problem using graphs. Yes?
Maybe according that we can think each pixel as a node, and as an edge we can think the maybe RGB similarity
between the two.
Between the pixels.
Very good. So one idea. Yeah.
Edges should be the inverse of the RGB difference.
Right.
So if the RGB difference is less, then the edges will be more higher.
Right. So in that case, what you're saying, so we can look at a similarity, okay? So we can define a similarity instead of a difference, okay? So one idea is that we can look at a single pixel, like a small pixel right here. It has a single value, for example, I don't know, 70, I'm just saying. And then like here, these values are like very high, like, maybe 180, okay? And then what we can do, we can compute the similarity between these two pixels, and this is how we're going to model our image. So there's another way. So this is one way, yes, of course, using pixels. We can also use what we call patch-based partition. So for example, here, I partition the image into different patches. So each square here represents a patch, and then what I do is that each patch here represents what? A node in my graph, okay? So in this case, if I build a graph that is composed of all these nodes, so this is a single node in my graph, okay? And for example, let's say this is a node centered at point xi. This is the center pixel, and then I have another node here centered at xj. So I can compute a similarity, the edge that connects these two nodes. Okay, this is not a good color. Let me use another color. So the edge that connects these two nodes is basically the similarity here defines my graph. So this is another way. Now, so this is how we can possibly use graphs to solve this this problem. However, what is the goal here? What do we want to do? If we use graphs to model this, imagine if two pixels or two patches that are neighboring, okay, we would expect their similarities generally, like let's say, to be high or low. Generally, if you're inside the object, if you avoid the boundary. If you avoid the boundary, you would expect that two neighboring or spatially neighboring patches or nodes to be highly similar. So the idea here is that if I learn how to compute this similarity, if I learn how to measure it properly, very accurately, then I can easily output, I can easily segment my image, okay? So this is the key assumption. The key assumption is if I learn properly the similarity between these patches, how similar they are, I know that those that are very similar, should have exactly the same labels. Okay, so the key idea here, the key problem is to find the similarity. Now, typically, one can use, for example, Euclidean distance. Okay, so you can compute the Euclidean distance between the vectorized patches, these two patches. That's one way. So here, our goal is to learn the similarity or edge weights between pairs of patches or nodes in the input image, okay, or graph, right? So why not use the Euclidean distance between two samples or patches? So here, when I say sample, it means patch. It can also, in machine learning, we use basically the term sample to denote a single instance that we will use and that we extract from our data. So here, a sample can be a patch or a pixel, right? So why not use Euclidean distance? What are the disadvantages of using a Euclidean distance? So if you look here, your patches, they have like lots of, pixels. So this is not a single value. This is, this belongs maybe to Rm. It has m pixels. So you have m values inside. You have m different values inside of this patch. Okay. So the problem is like your data, your samples, they live in a high dimensional space. So let me explain it here. So Euclidean distance, if we use it, it does not allow us to capture the geometry of high dimensional manifold where the data samples live. Okay, so for example here, this is the manifold of our data. This is like it's like a curved space or surface. It's a high dimensional space. Each point here in this space, this is a node, okay? Each data point or a node belongs to Rm, okay? So the problem is, if you compute Euclidean distance, if you have a manifold, what is the, if you have a space that is curved, what is the shortest distance between this point right here and the yellow point right there? So if you want to compute the similarity between these 2 points, which lie on a curved manifold or a curved space, if you use the Euclidean distance, it will give you this distance, right? So this is the Euclidean distance. So the problem with that Euclidean distance, it is not faithful to the geometry of the manifolds. Geometry, okay? So the geometry of the manifold here, it is curved. So this is like a surface. So we cannot use the Euclidean distance in this case because actually this is not the shortest distance. The shortest distance, the real similarity. If you use, for example, distance, so this is the real distance and similarity is a kind of an inverse, right? So in this case, Euclidean distance is not a good approximation. So what we want to do, we want to learn, okay, how to estimate the length of this path, okay, the length of this path that connects these two nodes I and J. The problem is that in machine learning, so you guys might not know, but manifold learning is really is one of the compelling research fields in machine learning, but it's not straightforward to construct the whole manifold and learn the geometry of the manifold. So to circumvent this, instead of like constructing the whole space and seeing how the space looks like, we say, okay, I don't want actually to construct this space. I don't want to know the exact geometry of my space, that it looks like this, but all I want to know is this distance, this length, okay, between nodes I and J. If I can get a good approximation of this length that is faithful to the geometry, the ground truth one, okay, so let's say this is the ground truth one, and then this is my estimation. If I get a very good estimation, then it means that I have approximated or somehow I have approximated or learned the geometry of the manifold, okay? So this is the idea. So this boils down to doing what, guys? If we learn how to estimate this, This is actually the similarity between the samples, and this is what we want to do. Okay, back to our story. So if we learn how to put these samples, place them in this space in such a way that similar samples, they cluster together, okay? So you can see here, we can easily find our objects, okay? Then it means that we have learned properly the similarity between these nodes. So here, Wij denotes the similarity that we want to learn, okay? It's the weight of the edge that connects, sample J to sample I. Now, why this is good? Why, if we learn the similarities in the original space, will enable us to output this segmentation map? Why is it the case? Where is it? Anyone? Because, yeah, these are very simple questions, but you guys need to know, the intuition and the logic behind these strategies, why we're doing this, okay? So the basic idea is that if I have two manifolds, okay, so this is, the image manifold, right? So this is the image space. And I have also the label manifold. The main assumption is that two similar samples, they will also share the same semantic label, generally. So this is, the main assumption. If these look very similar and my similarity is a very good measure, then I would assume that they will have similar labels, okay? So if we break down the images into small pixels or very small patches, so we will assume that these will have exactly similar labels. So that's the thing. So if we construct this manifold properly, the image manifold properly, then we can easily color and label images that are similar together based on this similarity, okay? So this is my graph, right? So now, how do we go about to solve this? So how to solve this problem? Now, we know what is the problem to solve. We know how to model the problem using graphs, okay? Now, the third question is how to solve this problem. And these questions are very current in when reading research papers and also when designing new solutions to existing problems. So the idea is that we want to learn sample similarity affinity. What we call similarity is also called in the literature affinity matrix for labeling the input image, okay? So here, this is what our adjacency matrix, right? So this is what we have seen before, so very simple. So we have different, our patches, our samples. These are our samples. And then what we want to do, we want to learn these values, right? We want to learn the similarity between these patches, all these similarities, and also the similarity between patches that are not very similar. Okay, now, as you guys notice in this example, I have, on purpose, I put similar samples together just in a blockwise manner, but generally it's not the case. They're going to be scrambled, okay? So in this case, if I learn the similarity, I will have a block diagonal matrix, okay? And what do you guys notice? That here we will have a very low similarity that is close to 0 between these patches, right? And for the similar patches, I will have a very high similarity that is almost close to 1, okay? So this is in the ideal case. Now, this means that I can, if I learn a very good similarity matrix W, then I can easily label my patches and get the output that I want, okay? So that's the basic idea. Now, how do we learn the W? If we find the W, we find the ultimate solution and we can output the segmentation map. So this is what the paper is about, okay? How to get the W. So here, the proposed solution is to use graph-based affinity learning or metric learning, so which means we want to learn the W, okay? Based on what? On diffusion. Okay, so this is the key idea. And actually, if you read the papers by Wang and co-authors, he has many papers published in CVPR and also Nature that are based on this basic idea. So one fundamental idea can give you many other good ideas, okay? So here the goal is to learn an accurate and faithful affinity map or similarity matrix. And this is important. Why accuracy is important? Because if you have an accurate similarity map, then you will have a very good segmentation accuracy. Okay, that's very obvious. Now, once W is properly learned, one can use a conventional segmentation method to partition the image into semantically homogeneous regions. Okay, so once you learn this one, once you learn the W, you can use any existing segmentation methods and or clustering algorithms to get the final result. So if you guys don't know about this, very simple, because many clustering algorithms are based on similarity matrices. If you give a similarity matrix that is simply based on Euclidean distance, it might not capture the true similarity in your high dimensional manifold, so that's not a good approximation. But if you learn how to improve the W, then your segmentation algorithm that takes in as input this similarity matrix will have a better performance. Okay, so this is, you know, the shared ground between many clustering and segmentation algorithms. So how to basically estimate the W? So they used graph self-diffusion, ST, and the good thing about the graph self-diffusion model that they use, it is able to capture both, you know, diffusion in general on graphs. If you keep diffusing iteratively like a random walker, you'll start from a local point, and we have seen this in the previous lecture. So you'll capture the local property and propagate throughout the shortest paths, like using a probability of transition, right? And then you will ultimately reach, you know, the ending points, all points in your graph. So the good thing about diffusion, it is able to capture both local and global aspects of your graph. Okay, so in his, like, if you read the paper, he was criticizing some methods that only focus on, they use local diffusion or any other local-based similarity learning method. So he said this method is actually able to model, capture these two aspects. Yes? A region growing, very good, yes. So region growing is, or label propagation. They're very similar to this. So the concept of diffusion is that you're starting from an initial point, and then you're like, yeah, you're propagating your labels. Yeah, right. So here, this works, you know, like this method basically, it works directly on the input affinity map and uses regularization in each diffusion iteration. Okay, so I'll explain a bit more. So what is the main assumption here? And let's look at this nice example. The assumption is that the local range similarities can be approximated by an accumulation of local similarities. And this is because of the propagation, right? So if you guys start from this point, and then you have one patch, another patch, and then you have many things like that. So you're starting walking along these paths, that what you notice is that the local similarities, if you accumulate these similarities, this edge plus this edge plus this one, you will get what? You'll get a long range similarity kind of between these two nodes. Okay, so this is the key idea. And here, look at this example. So what they're doing, they're using a diffusion, you know, their diffusion-based model. So this is the input image right here, and they want to basically segment these different objects, these ducts right there. So you can see that as the diffusion iteration increases, at some point we reach a threshold T star where you have a very good segmentation of the three objects and also the background. Okay, but if you over diffuse, then your result will actually worsen. Okay, so there is like some cutoff or some a particular number of iterations where your model will give you exactly what you want. Okay, so now how to model this? Let's look how mathematically they formalize this problem. So first, they have defined a graph G. So the set omega basically defines the set of samples, so they have n samples. So in our case, it can be pixels or it can be patches, okay? So it's a collection of data samples. W is the similarity matrix in Rn times n. And then Wij is basically, it's between 0 and 1 because it's similarity. So when you have Wij equals to 1, it means that sample I and j are identical, okay? Now, the next step, what they define, they predefine, they use here a Gaussian kernel, like as a first initialization of this. So they initialize using a simple Gaussian kernel, but then through the diffusion process, they are able to improve the similarity. So this is, you know, a first approximation of my similarity. So let's say, okay, Euclidean distance is not perfect, okay, but we can use it as a base approximation of my W matrix, and then basically learn how to improve it in particular areas or on the manifold that are not perfectly Euclidean. They're not flat. They're curved. Okay, so that's the basic idea, and the improvement will occur through the diffusion process. So this is what we have seen before. So this is simple. You have two samples, xi, xj. This is their distance. There is a kernel size. So a kernel size here, it tells us the distance is very important. So this kind of is a scaling process. So it's like it represents the scale at which we're looking at the data. So let's say if you have something like your manifold looks like this. So this scale is much larger than this one, okay? So here, what it's saying is that we're going to fix the scale at which we will look at our sample. So if you have here very small samples, this is a problem. So we're not look at this problem, but we will assume that generally our manifold has a similar scale. So maybe something like that. So I smooth it out and I have my points right there, okay? Great. So then what they define is what we have learned in the previous lecture. You guys remember this, right? So this is the transition kernel that we use when computing the diffusion base efficiency on graphs, and it's actually the inverse of the diagonal matrix of the strength of different nodes in the graph times the weight matrix or the adjacency matrix. Okay, so you can see that this is a diagonal matrix. We're summing over all columns, and we're getting the strength for each node. And just to remind you guys, previously we called it U, okay? So this is what we called in the previous lecture, but we had it inverse. Why is that? Because we considered that the random walker, okay, let me explain this so you don't get confused. So we have the random walker walking basically from J to I, and because we changed the direction, it's like, you know, transposing the matrices. So we got now basically the inverse of the strength matrix times W, okay? And Pij, the transition from node I to node J is basically equal to the weight between these two nodes normalized by the strength of node I, okay? Now, why we call this row-wise normalization? What is happening here if I have the matrix P? So if I have the matrix, let's say W, so simple. So I have the matrix W, Wi, okay, so we have 1, 1, Wij, etc. So what we're doing is that W2, 2, etc. So what we're doing is that we are normalizing each row, which means we're dividing the whole row by Si, right? This is row-wise normalization. That's why we call it row-wise normalization. And in such way, we get our transition matrix. So this represents what? You guys remember? Probability. Very good. The probability of a random walker going from node I to node J. Okay, so now what they introduce based on this matrix P, transition matrix P, okay, they define this iterative process, what they call the self-diffusion. So they iteratively update WT based on the previous similarity matrix learned in at T minus 1 plus identity, and the identity here they added for regularization. Okay, so this is for regularization. So this is exactly the formula that they have introduced, and then based on this formula, ultimately they will get the W star, which is the final learned affinity matrix, and they will also get the optimal number of iterations T star. So they're going to iterate over a fixed number of times. So the cool thing about this paper is that they have they found a closed form solution to this problem, which means they were able to identify exactly the number of iterations that the algorithm, okay, needs to output the desired segmentation, okay, and they proved it mathematically, so feel free to look at that in the paper. Now, the last question is why it works, and this is, you know, one fundamental question in research. So once you have an algorithm, it's important to know why your solution is a good solution. So there are multiple ways. Generally, you can have an intuitive explanation, say, well, this is, you can rationalize it, you can explain it intuitively, but a better way is to provide a theoretical proof that your solution is best or works very well, okay? So in their paper, they provide a closed form solution for estimating the T star, the optimal number of iterations for the self-diffusion process they defined on the graph, okay? So this is the algorithm that you guys will implement in your homeworks. So what you have here, everyone is looking now. Okay, so it's very simple. So you need to define the P, and then you will iterate. So first, compute the smoothing kernel. D is a diagonal matrix with a, so this is the definition, very simple. Then you perform smoothing for T star step. So you need to implement the T star, and the formula, the exact formula, you'll find it in the paper, okay? And then ultimately, after reiterating many times, you will do a last step, which is called self-normalization, and this is the final step, okay? Great, so this is the algorithm. Now, let's look at how this algorithm is able to solve many problems, including clustering and segmentation using diffusion on graphs. So, for example, you can see that here, each point represents what? It represents a sample. And the goal is to learn how to cluster similar samples together. So ultimately, if we learn a good similarity metric between samples, we will have all the squares together. And okay, now this is not a good one. Let's look at a good one. So we will have all the squares together, okay, and all the circles grouped in together. Okay, so this is learning our manifold, the similarity between samples. You can see that as you iterate, as the number of iterations, diffusion iterations increase from t equals to 10, so you can, you slowly converge to the solution until you get an almost perfect solution right here for T star. But then if you keep on self-diffusing for T bigger than T star, then your results, they worsen, okay? And then you can see that here they have, very nice results. So this is what you will also do. So I will give you 4 images. You will look at the images. For example, this is the input image right here. So it's a house. And what you will do, you will run a simple algorithm based on Euclidean similarity matrix. So you'll define your W in a basic way, okay, simple way. You will run a ready-made algorithm that's in scikit-learn, for example, to just, segment these images. So you'll get, for example, you can use normalized cut, right? And then what you will do, the only thing you will do, you will change the similarity. So you will apply the self-diffusion and put in the W star instead of the typical one, okay? And then see how the results improve. And you can see here that actually this is a very nice segmentation, because in this example, they were able to capture all these flowers, but here they were mislabeled, okay? And also in this example, another example in the paper, they used a random walk. So this is how they defined also another diffusion-based model. And this model is uses the random walker on a graph. So the random walk basically is of length t, right? If you guys remember, so we saw this before. And here, when they use the SD, the self-diffusion, you can see that they have very nice results because they can easily capture these lines, like all these lines, okay? So you can see that they have very good segmentation. Now, what you will do is first read the paper. So let me show you the paper. So this is the paper. It's quite, so it's like, not that long, but you feel free to, like actually you need to go over all details, but you don't need to do a lot of math, but you need to understand, the basic concepts to implement the homework and the algorithm, the self-diffusion algorithm. So this is, the choice of t. In this example, they explain how they found the optimal t star. And then they have lots of data sets, many experiments, and they show that their algorithm works on different problems. Now, after doing this, you guys will run it on a data set, so 4 different images that I will give you, and you will use normalized cut. So I'll share this link with you. So in normalized cut and scikit-learn, you give an image and it labels automatically this image into different parts, okay? But the key idea is that this uses a similarity matrix. So the similarity matrix, they compute it automatically. So you need to kind of run this algorithm, or feel free to find other codes. It's up to you guys. You can find your own resources. It doesn't matter. The most important thing that you take a segmentation, a simple segmentation algorithm, okay, that requires a similarity matrix between samples. Use the typical Euclidean matrix that we defined in step 1. Display the results, the segmentation, and then you're going to replace the W with the self-diffused W star and display the results and compare these 2 segmentation results. Okay, great. And yes, so that's it. Any questions?